Cool. Okay, so for today, then we're kind of moving into the applied regression in R and how to implement regression models. But before we jump straight into regression, I thought maybe just covering some of the basics that many of you have probably been exposed to in your basic statistics class or biometrics class, but maybe it's been a little while. And so we'll just go over some of these basic terms and concepts that are necessary for interpreting the flowcharts that are in this lecture that I posted online, this applied regression lecture. And so we'll go over those concepts. We'll talk about how to make decisions on testing for differences versus relationships. And these two concepts are the major concepts that you'll encounter in statistics. So typically you have two groups. You might want to know if there's differences between those two groups, or maybe you have more than two groups. Or you may have variables that were measured in concert or at the same time, and you want to test for relationships between those two. Okay, so differences versus relationships is one of the dichotomies that exists in statistics, and it's certainly a useful dichotomy for thinking about how to implement stats in R. Okay. And another dichotomy then, and then we'll go through this flow chart, okay? But so some of the basic concepts that you might hear is this idea of parametric versus non-parametric statistics. I remember one of my first job interviews, I was interviewing for a biologist position, and they asked me, what is the difference between parametric and non-parametric, and can you implement both of those types of tests? And the answer is, for parametric statistics, we're assuming this idea of normalcy, or a bell-shaped or Gaussian curve that we've talked about. And if the data follow a distribution like that, it's much easier to analyze those data, and it's much easier to interpret the statistical analyses that come from those. So I say these are the simplest to interpret and conduct. And you've probably already heard of some of these. So like the student's t-test, or the t-test as it's usually called, or the analysis of variance, or the ANOVA as it's typically called. These are analyses that are based on the assumption that the data that you're analyzing follow a normal distribution, a bell-shaped curve. Okay, but most of us in this class are ecologists, and we deal with data that don't always follow this assumption of normality. So we might have to use what's referred to as non-parametric statistics, or data that do not follow a normal distribution. They might follow a skewed distribution. We'll define that in a moment. Or they might follow a leptokurtic or a platykurtic distribution. We'll define that in a moment. And so most of the time, if you know a parametric analysis that's appropriate for your data, if they were normally distributed, there is a non-parametric counter to each of those analyses. And we'll go over those. We'll talk about the parametric version. How can you test to see if your data fit the assumptions of those tests? And then if they don't, what do you do? What is the non-parametric equivalent, okay? And one of the first ones that we'll talk about is this idea of kurtosis. And so we're thinking about data distributions here, and what this orange curve on the screen shows is a bell-shaped curve. We might have some continuous variable that we're measuring. Maybe it's the height of people in this class. And then on the x-axis is a frequency distribution, or a probability density function. Just basically an idea of how often those observations occur in a data set, okay? And so we can create a distribution, and we'll do some of this today. And we can create a normal distribution, or a Gaussian distribution. But the deviations from that may include a leptokurtic distribution that has a higher peak but shorter tails. That's one version that deviates from normalcy. Or there's a platykurtic distribution where the peak is lower but the tails are higher, okay? So you can imagine taking your bell shape and either making it really tall with flat tails, or very short with higher tails. And that's the concept of kurtosis. And I'll show you today in R how to test for kurtosis. Skewness is another one. So if you imagine here shown a normal distribution in orange where the skewness equals 0, but we might see a positive skew distribution where this right tail, or this tail going towards the larger values, or if this normal distribution was centered on 0, then the values to the right would be positive values. That's why you might see this as a positive skewed or right skewed. The idea is this tail is very long going in this direction. And then the complementary idea of that is this negative skew, where we have a longer tail going in this direction. Okay, so you've got the bell, but then you just kind of take one end of that and stretch it out. Okay, and so kurtosis and skewness are two of the main ways that we think about whether or not a distribution follows a normal distribution. Okay, and I'll show you how to test for those in R. Independence is another concept that you kind of have to have a basic understanding of when we're thinking about statistics. Independence describes a condition in which observations in a data set are not related to each other. Or in other words, one observation conveys no information about the next observation. So a lack of independence is where we start to move into what's sometimes called co-linearity or autocorrelation. Okay, so there may be observations that are related to each other, and sometimes we call those paired data. So an example would be if two of us were doing bird counts, for example, and we do bird counts at the same plots, but it's two different people making those counts. We could compare those two counts between those two observers, but we have to recognize that those observations aren't totally independent because the two observers were counting the same plots. Okay, so that's where we start to move into the realm of paired data. And you may have heard of a paired t-test before. And so we'll think about independence and what it means for the types of models that we fit. When we start moving into the realm of regression, if we have this issue of non-independence, we can account for that in models. And these are typically referred to as mixed models, which we'll talk about in a minute, where we have our fixed effects that we're interested in testing, but then we may have some underlying relationships between the observations that we could account for in a random effect. Okay, so independence, this is one of the core assumptions of linear regression, that the observations are independent. Okay, so you'll see that term a lot. And it's not necessarily related to independent versus dependent variables. Here we're using the term independent typically to describe predictor variables or X variables that represent the experimental variable that might be manipulated in a manipulative study or an experimental study, or maybe observed across some gradient if we're thinking about a natural snapshot experiment, for example. So if we counted birds and plots across a gradient of elevation. So elevation might be an independent variable that we're interested in relating to the number of birds that occurred in those plots, okay? And in that example that I just gave, the dependent variable or the response variable would be our count data. How many individuals are we counting there, okay? And you typically see the independent variable plotted on the x-axis and the response variable plotted on the y-axis. So sometimes these are called x variable or y variable. Typically, predictor variable or response variable is what you might see, okay? And so those data can follow either a continuous distribution. So count data, for example, would start at 0, where it's an absence of any individuals. And then they go up from there, and there could be any number ranging up to, you know, some definite number, some finite number. But then there's binomial data, which may represent presence or absence. So instead of counting the number of birds in a plot, we might say for a particular species, is it there or is it not? And this is where you'll typically see the term binomial. So there's two classes there. And this is used quite a bit in like logistic regression, where we have a yes or a no. Okay, so binomial, that's one of the terms that are in these flowcharts. Homoscedasticity, or which translates to having the same scatter, or sometimes known as homogeneity of variances. This is another assumption of basic linear regression or ANOVA type analyses. And I've given you an example here to the right, where we have relationships between two variables. So there's a variable here on the x and there's a variable here on the y. And notice that the scatter between those two is homogeneous or constant across the gradients of x and y. But notice here we have what's sometimes referred to as a megaphone type pattern, where it's very tight towards the lower, smaller values of x and y, and then it starts to go along this cone-shaped relationship. So if we were to put a regression line through there, the residuals around it would be much broader up here than they are down here. And so we refer to that as heteroscedasticity. And a lot of the parametric models that we fit, the ones that are traditionally well known, make the assumption that we have homoscedasticity. Okay, so that's another term that's important for thinking about: do we meet the assumptions to run a model, or do we need to think about a non-parametric equivalent of that model? Okay. Another term that's important is replication. So it describes the process of conducting multiple independent replicates of observations. And replication typically serves to give us increased inference or insight regarding the reliability of findings. So you might conduct an experiment along an elevational gradient in one basin, and then you might do it again in another basin. And if you find the same pattern there, that's an indication that your results are pretty reliable, that you have been able to replicate that. And so replication is important in statistical analyses because it increases our sample size, but also gives us some inference regarding reliability. And sometimes replicates are not fully independent. So if we made observations on the same experimental unit, so for example, we are measuring growth rate of an organism through time, and we're measuring the same individual, but we have multiple individuals, we can start to move into the realm of what's referred to as pseudo-replication, where we're making repeated measurements, but they're not totally independent of each other, either longitudinally or through time. And so there you might see this term pseudo-replication. And so sometimes in analyses, if we have pseudo-replication, we have to account for that non-independence in those replications within our model. And this is another area where these mixed models can come in and help us deal with that. Another way of dealing with that is nesting models, and that's what this next concept is. So we can think about making observations within field A, B, C, A, B, and C. And within each of those fields, there may be flowers, 1 through 5, and then 6 through 10. So those flowers occur within a particular field. They're nested within this field. And then within a flower, we might have seedlings that can be measured. And so seedling would be nested within flower. And so one of the ways of dealing with this idea of pseudo-replication is to just break down the hierarchical relationship or the nested structure of observations. So if we were interested in how seedlings differ across fields, we would need to take into account the fact that multiple seedlings may be measured from the same flower. Okay, so we can get at this issue of pseudo-replication by just building in a nested structure. Okay. And as you might imagine, these nested models can become pretty complex pretty quickly. And some of you I know are interested in mixed models or maybe hierarchical models. And so we can explore some of the R packages and functions that allow us to do this nesting. But this is a very powerful concept in ecology when we start to think about hierarchies. And hierarchies are everywhere. Okay. So mixed models, I've already introduced this idea. So this is where we can account for non-independence among observations by including what's generally referred to as a random effect that capture those relationships among observations. And then there's fixed effects that are usually pertinent to the hypothesis that we're testing there. So if we're really interested in fields and differences in fields, we might include flower as a random effect there so that we can account for these different flowers that were measured within each field. But we're really interested in testing how seedling density, for example, may differ between these fields. Okay, so in that case, field might be the fixed effect, and then we may have a random effect in there to account for relationships that we're not necessarily interested in. And usually, this is where we're violating independence. So we might have some sort of structure relating the observations. We want to account for that in our model by including a random effect so that we can test the fixed effects. Okay, so more on that as we move into mixed effects models later in the week. Okay, and I'm kind of assuming that you have a basic understanding of of a linear model, and if not, we're going to go through a simple linear model. And then we're going to go through generalized linear models. And so this is where we start to move from the realm of parametric regression to non-parametric regression. So we're not assuming that the response variable data, for example, follow a normal distribution. Count data are a great example of this. Usually, when we're counting specimens or wildlife or fish, in my case, those data can go down to 0, but they can't become negative. And there's usually a lot of low numbers. And so we get this distribution of data that does not follow a Gaussian distribution. We can use generalized linear models to get at that. And there's a number of different non-normal distributions that we can use, and we'll go through binomial, which we've already talked about. So if it was a yes or a no, we'd want to use the binomial error distribution. So outcomes of yes or no, only 2 outcomes. Usually for count data, the Poisson distribution, which would not allow for negative numbers. You can't go below 0 when you're counting individuals, but you can certainly go up in the other direction. So you have this very skewed distribution. And the Poisson makes a assumption that the mean and variance are equal. And so it's a very interesting distribution where as you approach 0, it becomes skewed. But as your data move away from 0, it eventually turns into a normal distribution where the mean and the variance are equal. But there's extensions of that, like the negative binomial, where we can add another term into the model where the mean and the variance are not necessarily equal. Okay, and if this isn't making sense to you, well, I can give you more details later. Some of you may be familiar with these distributions if you do a lot of count data. And the ecology, certainly count data are something that we think about a lot. And then the most extreme version of that might be a 0 inflated Poisson, where you're making counts, but most of the time there's nothing there, lots of zeros, and then you might see a huge number of individuals. And so I'll show you how to implement those distributions in regression type approaches in R, okay? Within linear models, within generalized linear models, and then there's additive models. And additive models are an extension of regression where we may not have a linear relationship or a curvilinear relationship. It might be that we have a very dynamic relationship. And so we can use these additive models that use splines or a moving window across the relationship so that you get these smooth, non-linear relationships. And that are typically, they could be Gaussian, in which case we're fitting an additive model, or non-Gaussian, in which case we're fitting a generalized additive model, okay? So we'll dig into these later in the week when we move into regression. But I wanted to start simple as we typically do and then move into the more complex ideas, okay? So if you can get a handle of on all of these terms, then you'll be able to go through and understand how to make decisions about which test to use, okay? So I've given you in this a list of tests of differences versus tests of relationships. And in this table, here's the tests of differences. So the G test, the chi-squared test, probably you've heard of before. Then I give you a description of that. And then we're going to implement those in R. And I'll show you which packages and arguments are used for those, okay? So this table is a list of tests that are presented in the subsequent flowcharts, okay? So the second half of the table is tests of relationships. Here's some examples of regression type curves, and I've given a link here to where I found this. It's kind of a comical representation of how we think about fitting curves in regression. And it's just showing, based on the same scatter of data, the black points don't change from panel to panel, the different types of curves that you can fit. So this is the simplest linear regression. And that's typically where we start. We want to fit a linear regression model. But as we start to violate assumptions of that model, we might have to go to fitting curvilinear models like a quadratic or a logarithmic or an exponential. Or we might want to go towards fitting a smooth. And we've already kind of seen this a little bit, but you can fit a locally weighted regression, which is like the generalized additive models do. This would be a linear with no slope, so it's totally flat. Here's logistic. You would typically not use this in a continuous response variable like this. It would typically be either 0 or 1. And then it becomes a bit more complex beyond that. There's piecewise regression, where you can break the data up into small linear segments and fit models to that. And as you might expect, this becomes much more complicated than we'll be able to cover in this course in a comprehensive manner. But if you know what type of model you want to fit to your data, then the challenge is just basically learning how to implement it in R. And we'll go over the basics, but remember, the point of this class is I want you guys to be able to identify a package or a function in R that you want to use. How do you load that library? And then how do you learn about the help resources to help you fit that kind of model, okay? So given enough time practicing in R, you can fit all of these different types of regressions. Of course, you would want to fit the model that is most appropriate for the data. This one was just a nice kind of demonstration of what different models look like when you hold the data constant. Okay, so then in subsequent pages here, I'm just giving you a flow chart. And this is something that you probably want to spend time with. And honestly, I get it. I know that you probably aren't going to spend time with this until you have your own data. That's when it means the most to you. And so I wanted to give you this as something that you could archive and come back to in the future to think about what type of statistical tests would you want to apply to your data. In the first question, are you interested in differences, or in this case, it's for choosing and using statistics? This is a flow chart out of a book that I read when I was first teaching statistics courses at another university. But it's a useful way of thinking about how do you make these decisions. So if you are interested in differences, so you have two groups or more than two groups, and you want to compare the means of those groups and ask if they're different. If your data come from individual observations, you can run this series of tests. If your data come from, and if there's multiple ways of classifying that, then you can go to figure 2. If data come from frequency distributions as opposed to individual observations, you could go to figure 4. There's a flow chart of ideas there, okay? So I won't go over this in a lot of detail. I basically wanted to introduce the idea that you make decisions about the most appropriate model to fit the data, okay? And that's a really critical thing to understand when you're running analyses. You fit the model to the data. You never fit data to a model. And so by thinking about the data to which you want to fit a model and asking some questions, you can determine what is the most appropriate model to fit to the data. So if you've got a single way of classifying data, so group by species, for example, you may have binomial data where it's 2 choices, or you might have polynomial data where there's more than 2 choices. Then you got to make a decision about, are the data independent or are they repeated? And so then if they are non-independent in this case, then are the data normally distributed, or are the data not normally distributed? And so by thinking about these concepts that we've gone over today and following this flow chart, you know something about your data. This gives, I think it gives students a little bit more of a grasp on the seemingly endless sea of statistical analyses that exist out there. If you know a few things about your data, these core assumptions, you can follow these flow charts and land on the most appropriate test. And then the question is, how do you implement that in R, okay? So if you're interested in, this is for tests of differences. And so if you're interested in tests of differences, depending on where the data come from, because there's so many questions to ask, I had to break this apart across multiple tables. But if there's multiple ways of classifying data, so you may have, we'll look at some of this fuel economy data today. But if you could think about different car makes or different drives or different classes of vehicles, there may be multiple ways of categorizing those. There may be 2, or there may be more than 2. And so it gets very complex, and you have multiple ways of more than 3 ways of classifying the data. Typically, you'll run a 1-way ANOVA, for example, or a 2-way ANOVA. So that's what this upper part is. And most of the time, it comes down to, is there replication or is there not replication? are the data normally distributed? And if they're not normally distributed, then you just use the non-parametric equivalent of the parametric test, okay? So these are the types of patterns that will emerge as you spend time with these flowcharts. Okay, and then tests of relationships. So that's for tests of differences. You want to know, for example, this distribution of body sizes from this type of environment, does it follow this same distribution of body sizes from a different environment, for example? That'd be tests of differences. But you may want to try and understand where those differences emerge from. And this is where tests of relationships can help you get at those ideas, okay? So then there's a flow chart for thinking about tests of relationships. Are you interested in associations without cause and effect? Or are you interested in associations with an implied cause and effect? And one of the things that you may have heard in your general statistics class is correlation does not imply causation. And so when you show a correlation between two variables, there may be an implied cause and effect there, but it does not always mean that there is a cause and effect there. And so that's one of the first decisions that you need to make. Do you expect there to be some causative relationship there that you might want to model? Or is it that there's no causative effect there? And so most of the time, you're thinking about some implied cause and effect. And so then you can go to 6. So we're interested in an association with implied cause and effect. So then you can ask, is the dependent variable, is it discrete, non-normal, or ranked? Is it a proportion or a frequency, or is it continuous? And does it follow a normal distribution? So once you get a handle of how to make these decisions about your data, it becomes pretty straightforward in terms of what statistical analysis do you apply. And of course, all of these can be implemented in R, okay? And the last one, what I'll end with here then is just the basic regression. So decisions for regression-based approach. I know some of you, when I asked early on, you said, oh, I want to run an analysis of variance in ANOVA, or want to run a t-test. We're going to get through that probably today. But some of you said, well, I'm interested in regression, but not a linear model. My data are more complex than that. I want to fit a model that accounts for non-independent, so a mixed model. Or I want to use a model that accounts for non-standardized variances. So then you might use quantile regression. So this flow chart will give you an idea of what types of regression models you might fit based on some information about your data, okay? So of course, you always begin with data exploration and decisions. What are the data that you're interested in modeling? How do they fit in with the hypothesis that you're interested in testing? And then once you've made those decisions, you've got a set of explanatory variables or a single explanatory independent variable, and then you've got your response variable or your dependent variable. And you've got a context in which you're interested in testing relationships between those two. That's where you would come into this flow chart. In the first, and remember, there's 4 assumptions of a linear regression model that you have to meet before you can fit a model. And one of them is independence, as we talked about earlier. Do the observations have no relationship with each other? Are they truly independent of one another? A linear relationship is another assumption. Can you fit a straight line to the relationship between those? If not, then you got to go towards nonlinear regression. And then the homoscedasticity or standardization of variances. If you fit a linear model through there, will all your residuals follow a normal distribution of variances, or do you have a scattering of data where you might have larger variances in some areas? Okay, so and then so linear relationship, independence, and then homoscedasticity, and then normally distributed data. Okay, so those are the 4. And you kind of walk through each of those here. So the first question that you come to is X, which is your predictor variable, or if you have multiple X's, are those fixed or are they mixed? So this is where, if it's mixed, you would go into mixed modeling. You may have fixed effects and random effects that you want to model together. Mixed modeling is the direction that you would go there. If you don't have mixed data, if X is fixed, then you ask the question, is the independence assumption satisfied? And if not, then you got to consider, do you have spatial correlation or temporal correlation? And there's models that you fit to each of those. And I'll explain these in detail and give you an indication of how to run those in R. If you do meet the assumption of independence, well, then you got to ask, do you have a linear relationship? If the answer is no, then you got to ask, is the normality and homogeneity assumption satisfied? And the answer is no there, then you run a generalized additive model. Or if the answer is yes there, you can run an additive model, which is this lowest regression that we're going to fit this week, okay? So remember, generalized is the term we use for regression models when we are dealing with non-normally distributed data. And then if it is normally distributed, then we can drop that term generalized, okay? If your relationship is linear, so the yeses, by the way, take you down the path of least resistance where you can fit a linear model, the most easily interpreted and fit model that's out there. The next question, if you do have a linear relationship, is do we have normality, homogeneity assumption satisfied? If the answer is no, then you go to generalized linear modeling. And if the answer is yes, then you can just go to linear regression, okay? And so, you know, if you're wanting to fit a very simple model, hopefully you hit the yeses all the way down and you can fit just a linear model. But as we deviate from those assumptions, as our data violate those assumptions, then we have to go off a different direction to fit regression models, okay? And this is what we're going to build up to with the coding session as we move into Thursday, okay? So that is posted as a PDF in Canvas. Please spend time with that. Specifically, you know, if you've got your own data that you're ready to fit some models to, let me help you develop those models in R. Some of you that are new to the program may not have your own data yet. So you'll want to come back to this later once you have your own data, because I do recognize it just means a lot more to you when it's your own data. But if you can, stick with me as we move through this, and you may be able to apply these things later as you collect data, okay? Is there anyone that wants to talk about any of this before we jump into implementing some of these more basic tests in R? Everyone's okay? I know that's a lot of information. Remember, you don't have to digest it all now. It's something that I meant to give you so that you can spend time with it as we move through the rest of the semester, okay? And it's always best to start simple and then become more complex. And that's exactly what you have to do as you start to understand how your data violate assumptions that are critical to the most basic models. And you always want to fit the basic model if you can, because those are the most interpretable and those are the most easily shared. As you start to move into things like a generalized additive mixed model, there's a lot of violations of the typical assumptions that have been made to cause you to fit a generalized additive mixed model. And they're hard to interpret. You got to kind of know what you're doing. You got to help your readers with understanding how the model is fit and what the output means. Okay, so there's nothing in the chat. Everyone's okay. We want to go ahead and open our studio and just start doing some of this stuff. I'll open mine here. And is there anyone that's having issues with R Studio or R? I know Ggplot was giving some issues 2 weeks ago. Is everyone okay? Caitlin, you're good?
No, I never quite got it figured out. So I was wondering if maybe I could come in early on Thursday and try and sort that out.
Let's do that. Yeah,
Okay.
yeah. Can you bring your computer? You want to meet in person?
Yeah, I'll come to College Station.
Okay, and you want to bring your computer that you're using?
Sure.
Yeah, okay, yeah, that'd be great. We'll get that worked out for you. It's an oddity. I know we'll solve it. It's not something that I typically see, but that sounds like a great idea Thursday.
Okay, I'll email you after class.
Okay, good.
Thanks.
Yeah. Everyone else doing okay? Ggplot is working. It's a pretty stable package, and what I mean by stable, is it's on the CRAN, which means it's gone through a lot of error checks. And then bugs have been fixed over time by Hadley Wickham, by the developer. And so, the longer a package is on the CRAN, the more stable they become in terms of throwing these weird curveballs at us like Caitlin's having to deal with. But we'll solve that, Caitlin, before Thursday. And I'm going to load some data from Ggplot, Caitlin, but they're the same data that I gave you in that CARS CSV file. If you want to load that from your working directory, instead of doing the Ggplot like we're going to do today, you can follow along with some of this early stuff. Alternatively, you and I can go over all of this together once we get Ggplot working for you. Okay, I don't want to leave you behind.
Okay, thanks.
We'll make sure that you're caught up. Okay, so I'm going to share my screen one more time, but I'm going to share the R Studio. Okay, and I'm going to close this, and I'm going to start a new one. Okay, so I'm going to start a new R script. Is everyone comfortable with RStudio and R scripts? And one of the things early on that I sometimes see is students aren't comfortable coding up here in the editor. They want to code directly in the console. Is everyone okay with coding up here in the dedicated script editing section? Okay. Okay. Well, so then let's start with just some annotation here, and we're going to load Ggplot too. Okay. And so Caitlin, we'll make sure this is working for you later. But remember, if you've already installed it, it's the function library, and then Ggplot2. An alternative is to go down to packages, click on packages. And then once that loads, you can go down to Ggplot2, and you can click that box there. And notice it ran that same line of code automatically. So I didn't have to hit run here. I was able to just click it here in packages. And what that does is it loads all of these functions from Ggplot2, but it also loads data sets that are built into that package. And one of those data sets, we can use the function data, is this MPG, that's miles per gallon. And these are the same data that I downloaded and put on Canvas 2 weeks ago and had all of you read those in using the read CSV function. And the reason that I want to stick with these data is that means that all of these examples that we're working through you can replicate these later if you want to go through this, if you're watching this recording months from now and you want to fit some of these models, you can learn how to do it on the MPG data. You'll have access to those. And then once you learn it on those data, then you just change the input data and learn how to apply it to your own data, okay? So if you run that data MPG, what you should see is an object MPG come up in your environment, and it first says promise. And what that means is it's loading the data from the package. It's going to show up eventually when we start to query it. Okay. Let me just open the chat here to make sure everyone's following along. Okay. Can't find the chat window.
There's nothing in the chat right now.
Okay, thank you. There it is. I don't know why it's not on the front of mine. Okay, holler. If you put something in the chat and I don't see it, always feel free to holler or chime in. I know some of you don't have a microphone, but if someone else sees something in the chat, let's just make it a community effort to watch that if you don't mind. Everyone's doing okay so far? You've got the data. If you click on this MPG, it's going to force it to load. So notice now that it has 234 observations of 11 variables. Everyone okay loading those data? We're just going to run some of these really simple statistical analyses on those, okay? Okay, so then let's just start by first plot a histogram. And remember, there's a couple ways of doing this. There's the hist function, which is the base function, and then there's the Ggplot function, and I'll show you both. Sometimes when you're coding on the fly, you don't want to make a nice graphic in Ggplot. You just want to see a quick and dirty plot, and the hist is one way of doing that. So let's go MPG. That's the object that we just created. Then I'm going to do the $sign. And remember what that does is it goes into that data frame, and it looks for columns. And we're going to spend time thinking about CTY, which is city fuel economy in miles per gallon for each of these cars. Okay, so we're going to say plot histogram of city CTY fuel economy. Okay, and it's just the hist function, open close parentheses. And when you're doing the hist function, you want to fit it to a vector of data. Remember, that's a single row of data. So we're picking a single column to plot the histogram. Okay. And if we run that, in your plot window, you should see a histogram that shows miles per gallon city on the x-axis, and then the number of vehicles that have that value in the histogram on the y-axis. Okay. And this is where you should see, under the assumption of normally distributed data, a bell-shaped curve there. We should see a distribution of data that follows a bell-shaped curve. And we can start now to think about, does this have a skewed distribution? Is one of those tails longer? Does it have a leptokurtic or a platykurtic distribution, meaning that the tails and the peak of the distribution have differed? Okay. And if you want to plot that in Ggplot, so then it's just Ggplot. Remember, you tell it the data up front, MPG. Then you tell it your aesthetics, which is the X and the Y. And in this case, we want to do CTY. We're only plotting one variable, so in the aesthetics argument, we only give it one. And then we can do plus, and we can do the geome. Remember, these are geometries for the shape of the plot that we wanted to make. And then we can do geome bar. Okay, so Ggplot, the data frame where we're going to pull the data, and then the aesthetics function, in this case city. Okay, and then geome bar. And if we run that, then we get a much nicer looking histogram. It's the same concept, but notice that the bins that it automatically puts it in are much smaller now. So we have a little bit more resolution of the data. And remember, if you want to go in and change the bin width, if you have a reason to believe that one particular bin width is important, you can do that within the geome bar function. Okay, there's an argument for bin width where you can change that. Okay. So now we have a little bit more resolution, and now maybe it's becoming more clear that we might have an elongated tail going to this side. And we might imagine that that's non-normal, but we can quantify that. We can actually test it. Okay. And let's start by testing maybe the normalcy. Okay. So let's see. Test if distribution is normal. Okay. And there's a test in R that we can do that. It's called the Shapiro-Wilks test. Okay. And so we can type in Shap, and it comes up with Shapiro.test. And what that's going to do, let me move this little thing out of the way. So it performs the Shapiro test of normalcy. And what it does is it compares your distribution of data to a normal distribution, an idealized normal distribution of data. And then it asks, is there a significant difference between those two? And so it does the test of a normal distribution automatically for you. So you can do Shapiro.test, and then we just tell it MPG and $CTY. So we're doing this test on a vector of data. In this case, the distribution of the city fuel economy. Okay. So everyone doing all right? So if we run that, it in your console, it says Shapiro-Wilks normality test. It tells you the data. It calculates the W, which is the test statistic in this case. And what it's doing is it's creating a distribution of data that has the same mean and standard deviation of yours. And then it's looking for differences between a normal distribution and the data that you have. And it's calculating this W statistic. Okay. And importantly, it gives you a p-value. And it's testing the null hypothesis that those are coming from the same distribution, a normal distribution. So if you have a significant result here, what that means is that your data differs significantly from a normal distribution. Alternatively, what that means is you have a non-normal distribution in the data, okay? A p-value here means that your data differs significantly from a normal distribution, okay? So we can already make a conclusion about these and annotate that and say data are not normally distributed. And that helps us with making a decision about whether or not we want to fit a parametric or a non-parametric model to these data, okay? So sometimes what you can do, though, is you can transform those data. A log transformation is sometimes helpful for fitting a normal distribution. And we can do the test on log transformed data by just doing the Shapiro test and then log on MPG of CTY. And what that will do is do a test of the log transformed data. We hit, and maybe before I test that, I can just show you what that looks like. So if we do a hist of log of MPG CTY, we run that. Notice it's pulled in, it's re-centered the data, it's pulled in that tail, and it's starting to look a little bit more like a normal distribution. And you might see that a lot in the literature. We log transformed the data to better approximate a normal distribution. And sometimes authors are very careful when they say that, to better approximate. That might mean that it's still not normally distributed, but at least it's closer to a normal distribution, okay? And we can test that using the Shapiro test of the log transform data. And when we run that, notice our W value, which was here 0.95, the W value is still pretty large, but our p-value is closer to non-significant. But remember that in statistics, the kind of typical rule of thumb is p of 0.05. If it's smaller than that, it's considered significant. If it's larger than that, it's considered non-significant. And remember, that's the probability of finding a value that is as extreme or more extreme than this W value. And so the probability has gone down, but it's still less than 0.05, which means even the log transform data don't totally fit this assumption of normality, okay? But they're better, it's closer. And so, you know, when you're fitting a model that assumes normal distribution, if you tell your readers that you log transformed it so it's closer to fitting that assumption, you might still be able to fit a parametric test. But really what this suggests is the most appropriate thing to do would be to use a non-parametric test if we were going to analyze these data, okay? We can test for other aspects of the data. We can also test for leptokurtosis. So does that have a high peak? Or we can test for platykurtosis, basically the kurtosis of the data. So if we, for that though, let's annotate this and say test for our test kurtosis. And there's a library for that. So here we want to use the moments library or the package. And I don't have that installed on here. And this is what tripped up a couple folks 2 weeks ago, is you don't want to install the same package multiple times unless you're updating it. So what I typically do is when I first want to use a package, I just go up to the help or to the toolbar at the top to tools, and then go to install packages. There's multiple ways of doing this. You can also do it from down here. But I like to go up to tools, install packages. I'm going on to the comprehensive R archiving network, and I'm just going to type in moments, and there it is. Okay, and what that's going to do is download that and install it into the library that's allocated to me on this computer. And I have install dependencies checked, which means that if there's any dependent packages that package is built on, it's going to also install those. Okay, And remember from last week, you're going to see a little bit of red text here. Red is sometimes warning and sometimes error. And warnings are not always a bad thing. Warning can be just a bit of information that it's telling you as it goes through the process of installing that package. And that's what we had it here. And then it tells us that the moments package was successfully unpacked and MD5 sums checked, meaning that all of the functions in that package should be ready to go, okay? So remember, for those that are new to using R, you only have to install that one time. It's now saved on this machine in my library. But every time I want to use it, I have to call the library moments, okay? Is everyone comfortable with that concept, those that are new to R? This is why R is such a powerful way of analyzing and storing and processing data, is because all of these packages that have been developed give you a lot of options in terms of the types of analyses that you want to run. And in this case, we're interested in running what's called the Ascombe test. This test. So notice as I started to write it in, it auto-filled it, and it tells me the package that it came from. It came from that moments package. And so if we had not gone through the process of installing that or running the library, we would not be able to find this function, okay? So it performs the Anscombe-Glenn test of kurtosis for normal samples, okay? So it's going to test to tell whether we have a mesokurtic or normal distribution, or a platykurtic distribution, or a leptokurtic distribution, okay? And then, so if I click on that, it populates the rest of the function, and then it starts to tell me about the arguments. And what we have to give it is X, and in this case, X is a vector of data. And in this case, it's the MPG $C. That's the vector of data that we want it to create a distribution. We could test it on the log transform data. We'll just test it here on the raw data. And what it's going to look for is a kurtosis value of 3. And if the value is 3, that's mesokurtic. That's a normal distribution. If the value is significantly less than 3, you're going into the realm of platykurtic. And if it's larger than 3, you're going into the realm of leptokurtic. Okay, so we can do this Ascombe.test on the vector of data. And what it tells us is the test that it's running. It tells us the data that it used. It gives us our kurtosis value. So remember, 3 is normally distributed. If it's higher than 3, then we're moving into the realm of leptokurtic. It's doing a statistical test on this value. How much does this value differ from the value of 3? That's your test statistic, or the Z value in this case. And then it gives us a p-value. And then our alternative hypothesis is that the kurtosis is not equal to 3, meaning it's not a normal distribution. Our value is higher, significantly higher than 3, so we have a leptokurtic distribution. And what that means is that the peak is, if we go back and do the histogram of just the untransformed data, what that means is our peak is taller than a normal distribution, and then our tails are lower than a normal distribution. We've got these outliers that are going way out there. Okay. So we don't have a normally shaped distribution, in part because it's leptokurtic. So we know it's not normal because we did the Shapiro test. Now we're starting to understand why it might not be normally distributed. In this case, because it's leptokurtic. But it may also be skewed, and we can test for the skewness of the data using a separate test, okay?
I have a quick question about this Anscombe test.
Very good, yeah, what do you got?
So in the little description for it, it said it was for normal samples. Is that not for normally distributed samples?
So it's testing to see if the sample is normally distributed. And if it's not, you'll get a significant result.
Okay, that was it's not a limitation of the test, it's what it's doing. Okay.
Yeah, exactly. You don't have to only use it on normal data. You're testing to see if the data are normal. Yeah, good. I know sometimes it takes a little bit of understanding what these tests are doing. That's why I wanted to run through them with you guys, because sometimes the null hypothesis is that your distribution is the same as normal, in which case a significant p-value means that you have deviated from the assumption. And sometimes it's the inverse of that. Yeah, but when it says a Scombe test for normal distributions, what it means is testing whether or not your distribution is normal. Great question. Is everyone else doing okay? You're able to run these tests and interpret the output? Okay. Let's do one more test of skewness then. And this test is the Agostino, and this is from the same, oops, let me move this out of the way. The D'Agostino test for skewness in normally distributed data. So it is the data, I see the confusion in the description there. What it's doing is testing whether or not your data follow a normal distribution. So it'll create a normal distribution, it'll compare yours to that, and you can ask whether or not the data are skewed. Okay, so we click on that, and the default, by the way, is always a two-sided test. And so sometimes you might have some information from the beginning that you would expect that the skewness is in one direction, so that it's that would be called a one-tailed test or a one-sided test. You might want to know if that right side of it or the greater side is significantly different, or the lesser side. You may have some information that you want to test regarding the direction of the skewness. Alternatively, if you don't have any a priori information on which direction should be different, you just run the two-sided test, okay? And so that's some basic stats I know that we didn't talk about, but the default is the two-sided, okay? So we just give it a vector of data again, MPG $CTY. And we can run that. And so now it tells us the data. It gives us a skew value. Notice that that value is positive. If it was negative, it'd be going in the other direction. There's the Z, which is our test statistic. And the larger the test statistic, the smaller the p-value. And notice it's giving us the p-value here in scientific notation. So this would be move the decimal over 6 places. So it'd be 0.0000005. Okay, so that's a very small p-value. So data have a skewness, and this is actually helpful, right? It tells you your conclusion. In this case, data have a skewness. It's a positive skew, and it's significantly different from a normal distribution. So this tail here, I mean, just by looking at it, you might have imagined that it had a positive skew on it, and we can test that using this D'Agostino test. Okay, is everyone doing all right? So if you have a distribution of data, and in my lab, we actually use these tests quite a bit. We have distributions of fish movement data, and we're always very curious. Is there more movement in an upstream direction, a positive direction? Is there more movement in a downstream direction, a negative value? Is there a lot of stationarity to it? Does that mean, is it leptokurtic? Is there a lot of observations around 0 and not very many that are going out? Or is it a platykurtic distribution where there's a lot of dispersal happening? So those that are interested in movement of organisms, if you've got a two-dimensional, in our case, it's upstream or downstream, you may be using these. Or you may be thinking about distributions of, well, actually, is there someone in the class that's interested in running these types of tests? Is there someone that thinks about normal distributions of some particular variable? I find it's helpful to give real life examples, and I love hearing about the research you guys are doing. Is there anyone that has an inkling of insight that you might use this test? All right, we'll move on then. So it is an important test to understand if your data are normally distributed or not. Amy, were you going to add something?
I do have a quick question. So you said that you use it in your lab for fish movement data.
Yes.
One of my lab mates and I are currently doing an experiment with flies, but it's kind of their preference on a gradient of different chemical compounds. So is that another thing that this could be used for, or?
Yeah, so yeah, I'd love to hear more about it. You've got a gradient of chemical compounds, and then you make observations about the number of flies that are on each of those compounds. Is that correct?
So we have one fly isolated in a petri dish, and then within that petri dish, we'll take a filter paper and have it divided into 4 quadrants.
Okay.
Well, I guess, yeah. So each quadrant has a different compound on it. And what we're trying to do is assess how much time the fly spends on each quadrant to see if there's a preference.
Yeah, okay. Yeah, so you quantify how many seconds the fly spends on each of those compounds?
We're trying to, yeah.
Okay. So you may be able to produce something like this, where it's compound 1 through 4, and then it's the amount of time that they spend on each of those.
Okay.
And your hypothesis is related to preference for a particular compound, or?
Yes. So a little bit of background, my lab mate and I, we work on black soldier flies.
Mm-hmm.
And so we're trying to see if whether or not certain compounds are present, if that increases or decreases the likelihood of mating.
Okay.
And also if compound strength has anything to do with that.
Okay.
But we were going to try to use EthoVision to even collect the data. We have the videos, but our professor that we were going to work with on that, his lab flooded. So.
Oh no! Oh,
yeah,
I'm sorry to hear that. I heard entomology had some major flooding.
Yeah, it's pretty bad. So.
Oh, I'm sorry to hear it interrupted your research. Hopefully they're fixing it.
We'll see. I don't know if they're going to demo it or not. The ERL building's pretty worn out. The water ran for 2 days before they could shut it off. So.
Well, based on the description that you just gave me, what you might want to test for is do the distributions among those compounds differ from a uniform distribution? So if there was no preference, you might expect that time is equally split among all of those. We're kind of moving into the realm of goodness of fit tests, which I think is what you would want to apply. So maybe what we can do today for the last little bit is let's move into goodness of fit tests, and then we'll expand more on this, Amy, in the context of your research, because this is really cool. You actually can use some of these basic stats to get at that question. So let's, before we end for the day, we end at 12:45, is that right? Mm-hmm. We've got about 5 minutes. Let's introduce the idea of a chi-square test, the kind of first goodness of fit test, okay? And so to do that, why don't we just, for the last thing that we do today, go for test for differences in the number of cars in each class between 1999 and 2008, okay? So there's multiple classes of cars in this data set, and there's observations from only 2 years, 1999 and 2008. They did a query of cars in those 2 years. And so let me show you what those data look like. All right, so you can do the function table, then you can do MPG, class, and that's and we'll talk about that in a minute once we plot the levels. And then there's MPG year, okay? So the table function is going to go into MPG, and it's going to summarize the number of cars in each class between the 2 years. All right, so I'm going to hit run on that. I'm going to bring this up just a little bit. And so here's the distribution in 1999, and here's the distribution in 2008. Two-seaters. There were 2 of those in 1999, and there was 3 of them in 2008. And so, Amy, you might have, instead of cars, you may have your different compounds here. And you might be interested in comparing an observed versus a predicted distribution among those compounds. And your predicted distribution might be uniform, like there should be an equal number in each of those. And then your observed, if there is a preference, they might spend a lot of time in one particular compound. Okay, so this is what we typically refer to as goodness of fit tests. Do these data, in this case, the count of cars, in your case, it might be the number of seconds spent in compounds, do those come from the same underlying distribution? So we want to compare 1999, and in this case, with 2008. Did we see more pickups or did we see more compacts? And you can see the numbers differ a little, 25 compacts versus 22 compacts. But if we compare the distribution in these discrete classes, is there a difference between those two? And that's where a chi-squared test comes in, and it's a goodness of test. And what we can do, if you typed in this table, MPG class, MPG year, you can nest that within the chi-squared test function, which is CHI SQ dot test. Okay. Sorry, I got a tickle in my throat. And oops. Very good, thank you. So if you misspell that, that's pretty critical. And notice the error, it could not find function chi-square dot test. So that actually would have been interpretable if someone had not pointed out that I typed in the wrong letter. Okay. Okay, so it gives us, notice there's still red text down there, but that's a warning message and not an error message. That means it ran. So Pearson's chi-squared test is telling us the data, and it's looking at the difference. It's telling us the number of degrees of freedom, and then it's giving us a p-value. And what it's doing is it's overlaying those two distributions, and it's looking at the major difference between the two. That's this chi-squared value. And so on average, there's only one difference in the number of cars between the two classes. And what that means is here, the p-value, the probability of finding a value as extreme or more extreme than that chi-squared value, is pretty high, which means that's a relatively small difference between the two. And so what we can conclude is that the distribution of the number of cars between those classes did not differ between 1999 and 2008. Okay, this is a goodness of fit test using here the chi-squared test. And let's stop there for today because we're running out of time, and we'll pick up there on Thursday, and we'll finish off the kind of comparison and basic ANOVA stuff, but then we'll move into the realm of regression. Okay. And so on Thursday, what we'll do is, if you want to just save this script that we've started, we'll go through that again. And hopefully everyone is able to code along beside me. If I'm ever going too fast, please just say slow down, and we will slow down, or I will slow down. But we're kind of moving, I think, into the realm of stats that may actually be used by folks in the class, Amy in particular, based on that study that you described. Sound like a plan? So we'll just hit pause there for the day.
I had a question.
Oh,
Did you
good,
say
yeah.
we have an assignment due on Thursday? I think I got confused at the beginning of class.
There's no assignment for Thursday.
Okay.
Yeah, thank you for clarifying that. Yeah, they didn't, based on my interpretation of that email, the university is understanding that many of you are probably way behind on things, and adding exams or things that are due is not like in your best interest right now. So I'm not going to make you turn this in. We'll just go through this stuff. I mean, the whole idea here is you get out what you put in, and if you don't have time to follow this stuff, you might not be getting much out of it right now, but I understand that you may be just totally covered up with stuff because of all of the delays caused by last week. So at the end of Thursday, I will give you all of this in a nice annotated script, so you don't have to turn anything in on Thursday. Yeah, thank you, Natalie, for clarifying that. Everyone else okay? I think I was telling Sarah that I think the theme of this semester is just patience. We just gotta patience with the process, with all of the just curveballs that have been thrown. I want to help you guys, not like burden you with a bunch of stuff that maybe you don't have time to take on right now. But and the other thing is, I just want to provide stuff that you'll use either in the short term, but more likely in the long term, right? Yeah, cool. Okay, so there's not going to be an assignment. We'll just come back Thursday. There won't be a lecture. You can spend time with those flowcharts that I gave you today, in the context of exactly what Amy is doing, thinking about how you might apply this to your own data. I think that's a great use of time. And then we'll just go through some of the more advanced stuff on Thursday. And there's plenty of room to come to class if you're interested in doing that. But I'll do the same recorded live Zoom session as well if you're not interested, or if you're remote. Okay.
Thank you.
Cool.
Thank you.
Yeah.
Thanks.
Yep. See you, gang.